So the next version of our dictionary implementation is going to be using a hash table. So hash tables are extremely useful because they give us constant time. They give us constant time dictionary operations. So that's searching and inserting and deleting. These are all constant time using this particular data structure. So that's very, very convenient. But the important thing to note is that with our implementation, we're talking about this is actually going to be constant time on the average case. So we'll just talk about average case. But if you want sort of guaranteed and provable worst case constant time, then you can look up something called cuckoo hashing, and there are a bunch of ways of hashing out there. Like there's universal hashing, cuckoo hashing, and all these other ways of hashing. But for our purposes, we're just going to look at an implementation of hash tables, which allows us to perform these dictionary operations in constant time. Okay, so now keep in mind that we did talk about these balanced BSTs and how we can use them to implement a dictionary, and those were all logarithmic time operations, but they gave us a few more operations than these hash tables can, right? So if these three operations are all we need, then yes, we should use hash tables for this sort of very, very quick runtime. But if we want something more than that, like say we wanted to find a successor or a predecessor, then hash tables kind of give us nothing over BSTs, right? BSTs are rather much more useful in that context. So BSTs aren't completely obsolete now that we've seen hash tables, but they're just something more useful for these particular operations. Okay, so that being said, fun fact, Python dictionaries are also implemented using hash tables because of the fact that, for these particular operations, hash tables are really, really quick, and hash tables show up a lot in things like InfoSec, with cryptography and spell checkers and caching, and they have a bunch of uses. So it's good to learn them. So now we want to talk about implementing a dictionary, and in particular, we will talk about implementing them using this array called a direct address table, right? So this thing right here is called a direct address table. Or rather an array. So a direct address table is just an array where each of the keys in the dictionary produces some index into the array. So keys produce indices, right? So keys produce indices into the array. Okay, so all right, so that's good. Keys produce indices to access certain spots in this array. But what if we have some kind of key that says something like hello? What if this hello, which is a string and not an integer, what if this is used as a key, right? Because this could very well be used as a key, but it's obviously not an integer, so how do we use it as an index? And also, think about how long this array would get. right? Think about how long this array would get as we add more and more keys, right? We'd have a super big array if that was the case. So these are a few problems we see right off the bat using this direct address table. So instead of a direct address table, let's actually solve these problems using a hash table. Okay, so a hash table, just building on top of this idea of a direct address table. Say now we have some universe of all the valid keys we can have, right? So this thing right here is going to be okay, so this U is going to be the universe of all valid keys. Okay, so this U is the universe of all valid keys. So any key we think of, it comes from this U. Okay, so you can think of U as some kind of set which contains all the valid keys you can have. Now, a hash table, you can think of a hash table as this kind of array, right? This is, let's call this array A. So this is some kind of array, and let's say it has m spots, so it has m positions, or m slots, or m buckets. Each one of these is called a slot or a bucket. Slot or bucket, right? So it has m of these slots or buckets. And okay, so now the other thing we need to talk about is there has to be some kind of function that we can use to map the keys to an index in this array, right? So what can that be? So let me actually write it down here. So we need a function mapping keys from our universe to to the set of, or to any position here. So to some index, I guess. Yeah, if that makes sense. So for those of you with a bit of background in math, we can sort of represent this as this function h mapping u to this set 0, 1, all the way to m minus 1. Right? Hopefully you can see this is an m. So yeah, this is all the indices we can have. This is a universe of all keys, and this is the function that maps our universe to this set. Okay, so that's what the hash function signature is. Now, what does the hash function do? Well, hash function does two things. So first, what it does is it converts our key to an integer, because remember, using open addressing, what we said was, say we have a string such as hello or something, we can't assign it an index in our hash or in our open address table, because it's not an integer. So how do we assign it an index? And this is what we're solving using this hash function. And the second thing we need the hash function to do is to compress the integer to a small range, which corresponds to the buckets in the hash table. So yeah, so if we have m minus 1 or 0 to m minus 1 as our range of indices, then it needs to compress the integer we get to being an integer within that range from 0 to m minus 1, so that it corresponds with some index in our table. Okay, so now we notice that we can have multiple keys hashing to the same slot, right? So when this happens, we call it a collision, right? So if multiple keys hash to the same slot, we say that we have a collision. And in fact, collisions are the reason why we store all our objects in a particular bucket within a linked list. So we can chain them up, right? So this is the idea of chaining. Store things hashed to one given slot within a linked list. So that's the idea of chaining. Okay, so now that we have this, okay, so we have this, and we can therefore insert at the head of the linked list, right? So we have some kind of linked list, and we will insert at the head of the linked list, so that it kind of looks something like this, I guess. If I want to draw a picture, let's say there's some index we're inserting into, and at this index there's a linked list, right? And we insert at the head, so the thing that was there moves to the next spot, and this thing moves to the next spot, and so on. Well, it doesn't really move because it's a linked list. It just we just add to the head of it. But this is sort of the picture, right? We add to the head, and we just increase the size of this linked list according to that. So this is chaining. Hopefully that's a good visualization. Now notice if we have n objects, so for n objects, we can do these dictionary operations. So search for some key. Well, it searches the linked list at the index h of k. So we apply the hash function on our key, and it'll give us an index within a small range. And once we have that index, we go to that index and we find the linked list. And once we have the linked list, we just search through the linked list, and we have an idea of how that looks like, right? This is O of the length of our linked list, right? So we go through all the elements in the linked list. So that's O of the length of the linked list. So searching is therefore O of the length of our linked list. What about insert? So we insert some key. Okay, so when we insert it, what happens? Well, we insert into the linked list at h of k, right? So at index h of k, we find a linked list and we add our thing to the head of that linked list. Okay, so first, however, we need to check whether that object already exists in the linked list. So we insert into the linked list at h of k after performing a check to see if it already existed before. Okay, so this is also, once again, O of the length of our linked list. Okay, so how about this delete? So we have this delete operation. We delete a key. And this is going to be, well, we delete from the linked list. And this is at h of k. So at the index h of k, we delete from the linked list something corresponding to the key k. So once again, we would have to first find the key k in the linked list. So this is, again, O of, just to be consistent with what we did before, this is going to be O of length of linked list. Okay, so we have all three of these operations taking O of the length of the linked list. So that's interesting. What kind of length are we looking at then? That's the question we are interested in. Right? We want to minimize that length for that runtime to be not as large. So notice that all these operations do require us to go through the linked list in some way. So it's all O of the length of the chain. But if all objects hash to the same index, this is O of n for n objects, right? So say we do have some kind of pathological inputs, then this can be O of n potentially for n objects. Okay, so this can be O of n potentially for n objects. So our dictionary operations are O of n in the worst case, which is certainly not what we set out to improve with. Remember, we wanted O of 1, or rather theta of 1, right? Constant time operations is what we want, but we just found that this can be potentially O of n. Okay, so let's look further. So for everything to hash to the same bucket, we must have really poor inputs, right? So this should rarely happen, and under certain assumptions, we find that we actually have O of 1 average case performance. So we need to make some assumptions. So assumptions need to be made. And how reasonable are these assumptions, and what kind of real work that goes into making these assumptions work. That's something we will talk about, but we need to make some assumptions in order for us to see that this is going to be in O of 1 on the average case. So again, though, this should rarely happen, right? Rarely should we see that we have a chain that's almost that's so long that it's almost as many keys being hashed, which is same as the length of the chain. But anyway, like we said before, there are hash tables out there that also guarantee worst case O of 1. In this case, we'll make some assumptions that guarantee average case O of 1. Okay, so average case of search. So for the search operation, let's take a look at the average case. Key is first of all chosen uniformly at random from our universe. So we get some key uniformly at random from our universe, and we assume that we have simple uniform hashing. Assume we have simple uniform hashing. Okay, so actually, what does this mean? Well, every key is equally likely to hash to any okay, so any key is equally likely to hash to any of our m slots. So for that reason, the probability of hashing key k to some bucket j is 1 over m. Hopefully you see why. Because of this simple uniform hashing, we have 1 over m as the probability of hashing some key k to some bucket, some arbitrary bucket. And that applies to any bucket, of course. Okay, so now we add the times. So add times taken for, first of all, computing our hash h of k, and second of all, also traversing the linked list at index h of k. At h of k. Okay, so this first one, okay, all right, so this first thing here, we assume that that takes place in O of 1 constant time, right? That's our assumption, and we'll look into that in just a bit about how we make this hash function. But the second one right here, that, what is it going to be? Well, let me move all this up a little bit so we have some space. Okay, so this second part here is going to be O of alpha, or O over n over m. So O of alpha or O of n over m, and this alpha or n over m, this is actually known as the load factor. So this is known as the load factor. And this load factor, first of all, n is the number of keys we have, and m, okay, so m, we know what that is, but 1 over m is the chance that chance of hashing, the probability of hashing k to some bucket j, as we said before. So is the probability of hashing to some bucket. To some bucket. And so if we multiply the two together, we get n over m. And what does that represent? Well, it represents the number of keys that get hashed to a given index, right? So represents the number of keys hashed to a given index. Okay, so that's what this load factor is. Nothing except, it's nothing but the representation of the number of keys hashing to a given index. Okay, so the average case for search, the average case for the search operation is going to be theta of 1 plus alpha, right? So this is the load factor we talked about, and this is the constant time assumption we made for the hash function. So this is sort of the runtime we get, and remember this alpha is for when we traverse the linked list, and this 1 of 1, it was from the actual hashing we did. Okay, so now notice that if n is less than m, then this implies that the runtime is constant. So we have theta of 1 runtime, and okay, so that's if the number of keys is less than the number of slots. And we also have that if, let's say, n over m, the load factor, was some constant, then we also get theta of 1 runtime, right? So if theta of 1 runtime applies when there are more slots than keys, or if the load factor is constant. In both cases, we get constant time. But when do we not get constant time? Well, if n over m grows proportionally, so if this grows proportionally, I should say grows proportionally to n, if this grows proportionally to n, then if that's the case, then we don't have the, 1 over 1 we don't have, so our runtime is not in theta of 1, right? We don't have constant time, and this g of n represents the running time of our implementation of our algorithm. Okay, so what is the solution? How do we solve that last issue we just talked about? And we have a solution. The solution is that we choose m large enough that we can guarantee some constant time average case, or we dynamically allocate memory to expand the size of our hash table. And this is usually, this requires some rule of thumb, like if it gets pretty close to being full, then we double the size. Maybe if we have 3/4 of our slots filled in, then we double the size. But basically, it's all based on how you want to double the size and when you want to do this. So yeah, but this would be a valid solution, and this would also give us constant time in the latter case. So now, okay, so now, oops, just notice there's a typo here. Okay, so now we remember that we have to approximate our original assumptions. So we need to actually select a good hash function. We made a lot of assumptions, right? And to approximate them, we need a good hash function, because we said hashing would be constant time, and we'd have a good hash function so that, well, you'll see what that means in just a sec. But yeah, the important thing to note is we made a bunch of assumptions that we need to make sure we are not just assuming something and we don't satisfy any conditions to meet those assumptions. So that's why let's take a look at how we design a good hash function. So we can use the binary representations of objects in computers, right? In machine code, everything is represented in binary, so we can actually take those binary representations of these objects, and we can produce integer keys. So we take the binary representations of objects in computers, and we produce the corresponding integer keys. Now, these keys can be very large. And with Python, if you take a look, if you just if you do hash hello or something like that in Python, is a huge integer, right? So Python has this built-in hash function, and if you do something like this where you hash hello in Python, that's going to give you a huge integer. So what else do we need to do? Well, we need to so the integers that we get might be very large, so we must have some way of mapping. So we must map the large integers to the range 0, 1, and so on until m-1. Right, so this is precisely the range of all indices in our hash table. So that's where we want to be at. We want to map all the integers we get that are keys, and we want to map them to this range using our hash function. So, okay, so first we need our hash function to use all bits of our key k. So this best ensures to best ensure that that different keys lead or produce different hashes. And the second thing we want is that, okay, so we want h of k to spread the keys around to all the baskets or buckets. And the third thing we need to make sure is h of k should be efficient. So remember how we said h of k takes, or our hash function takes constant time? Well, we better make sure that it indeed is constant. We don't want to say it's constant when really it doesn't take constant time. So, okay, so these are the heuristics, or the following are the heuristics we need to meet these requirements. So, okay, so actually we need some heuristics to meet the above requirements. Okay, so hash functions that seem to work well. So we need heuristics in order to produce some hash functions that work well. Okay, so maybe I'll move this up. Okay, so the first way we'll talk about is called the division method. Okay, so the division method is something like this. So first we have h of k equals k mod or actually let me do k mod m, and this is going to be in, because we mod it with the number of slots we have, this is going to be in 0 to m minus 1. So it'll live within the range we need it to live within, and the effectiveness of this actually depends on the choice of m. So how many slots there are determines how effective this is. So we have another heuristic, which is to choose m to be prime. So choose m to be prime. So if m is prime, then our hash function will perform somewhat better than if, especially if m is something like a power of 2, right? Because think about what happens if m is some kind of power of 2. Then we mod something with a power of 2, and we might only get returned something that's like log base 2 of m, lowest bits of our key. So we might just get log base 2 of m, lowest bits in this key, if m is something like the power of 2 or something. But if it's prime, then we won't ever have a problem like that. Okay, so so now that we have that, we actually have this one variation of the division method that I will mention. Variation of the division method, and this one is actually used in universal hashing, and this is how it goes. So h of k equals a times k plus b, and all that we mod with m. Okay, so if you actually look at the Introduction to Algorithms textbook, the CLRS text, you can see this. If you want some more details, you can research a bit. But yeah, this is actually a variation of this division method. Okay, so the second way we want to talk about is the multiplication method. And the multiplication method goes like this. It has h of k equals, and this time we're flooring, m times k times, okay, so now we have this constant a, and this constant is in this open interval 0 to 1, and this is going to be modded with 1. Okay, so alright, so this mod of 1 actually returns the fractional part. Fractional part of a. So that's what that a mod 1 will do. And there's this guy named Donald Knuth. And if you're in CS, you must have heard his name several times, but he's a very important figure in CS. He's actually the guy who invented the LaTeX language for typesetting documents beautifully. But anyway, what he suggested was that we choose a equal to root 5 minus 1 all over 2. And he said that this right here is a pretty good choice for a, this a constant. So yeah, that's what he said, and I guess a lot of people might have been convinced, considering just the fact that he is Donald Knuth. Anyway, so the benefit is that with the multiplication method, we have the benefit that we aren't relying on the value of m anymore. So before we said that this m had to be a prime number because you know, you could throw things off if it was something like 8 or something, but now we aren't relying on the value of m when we use the multiplication method. So that's good. Now we want to look at something else completely. We want to look at open addressing. So open addressing, now we're moving away from this chaining method that we were discussing until now. And now with open addressing, what do? Well, we resolve collisions like with chaining, but we do it in a sort of a different way. So we first find the next free bucket to avoid collisions, and actually what we do has a name, and it's called linear probing. And this isn't the only kind of probing. There's also other kinds. You know, you could do quadratic probing or cubic probing or other kinds of jumps, but that's actually, you don't even know yet what this probing probably means. So let's actually talk about it, and then we'll address the other ones I mentioned. So with linear probing, how that works is we have h of k. So we have h of k plus I. H of k plus I, and all that we mod with m. So h of k plus I mod m, where so I is in 0, 1, and so on. So from I starting at 0 all the way down, this is linear probing, and it can actually lead to long probe sequences. What do we actually mean by linear probing? Well, say we have this hash table, and this spot is filled, and this spot is filled, but this spot is empty. Then let's say we insert something at this is index 1, this is index 0, this is index 2, this is index 3, and this is index 4. Okay, let's separate that. Okay, so yeah, so now let's say we do h of hello, right? And this returns 1. So we try to put it at 1, but in the case of open addressing, we will not have a linked list at each index. Instead of chaining stuff, we will look for a free slot. So we go here, we see that this is taken, so we go here, we see that this is taken, we go here, and we see that this is not taken, so we will occupy this slot. Now it has been taken. So this is the idea behind linear probing. We go linearly, so one by one. So first we go here, then we go here, 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 and so on, like that. We go linearly as opposed to, jumping like quadratically or something cubically or something. We don't make big jumps, but rather we make linear jumps. So yeah, that's the idea behind linear probing. Now, okay, so that's linear probing, and as you can see, if we had a bunch of x's here, we'd have to make a lot of jumps, right? So that's why we say this can lead to long probe sequences. Now, there's also something called quadratic probing. Oops. So quadratic probing. And with quadratic probing, we jump longer distances. So we can jump longer distances, and we can do something like h of k plus, some constant c I plus another constant d I squared, and then all that we can mod with m. And once again, we have this I equal to 0, 1, 2, and so on. So this, if we do something like this, this is quadratic probing. So we make much larger jumps, and instead of going at each next index, we jump several indices. So we don't have extremely long probe sequences. But with quadratic probing, clustering can still happen, and choosing C and D without any thought, careful considerations, choosing bad C and D constants can also lead to unused slots. So let me actually write that. Choosing, or rather, bad choice of C, D leads to unused slots. Okay, so we do have to be a little careful when we choose C and D. Okay, so that's quadratic probing, and also we have double hashing. So double hashing, right, we have something that looks like this. So we have not only one hash function, but rather we have a second hash function, right? So it's I multiplied by the second hash function applied to that key, and now we mod that with m. Okay, so once again, we have I equals 0, 1, and so on. And in this case, we use two hash functions, and therefore two sources of randomness. So using the more hash functions you use, and the more hashing you do, this entire idea with hashing is just to sort of stir things up and output some kind of random integer. And the better we do that, the more we can guarantee we can find, or not guarantee, but the more likely we are to find some kind of unique index to hash into. But anyway, each key we see starts at h of k and has the jump sequence corresponding to h2 of k, right? So it starts off here at h of k, and initially I is 0, but then if it's taken, then we have this jump sequence, h2 of k, and then 2 times h2 of k, 3 times h2 of k, and we have a jump sequence that goes something like that. So that's also interesting to look at. Okay, so all right, so let's actually look at the performance of open addressing. So we do some analysis. All right, so let's do some analysis. Okay, oops. So we get 1 over 1 minus our load factor steps for unsuccessful search, and we get 1 over our load factor multiplied by the natural log of 1 over 1 minus our load factor for successful search. And these are both on average case. All right, so let me actually write that down properly. So this is the number of steps for unsuccessful search, and this one right here, the steps for successful search, and both of these once again are average case. So how did we get this? Well, I can post the link to the sort of the appendix that shows the derivation, but yeah, just for the sake of time, we won't go into how these are found, but this is the analysis for open addressing. We have the case where we have a successful search, and we have this many steps, and for unsuccessful searches we have this many steps on average. Okay, so with open addressing, it must be less than 1. So the load factor, I guess I should say, this load factor must be less than 1, right? For open addressing, or else the table is full, or table full, right? So if the table is full, then we have no choice but to chain, but then we're not doing this open addressing anymore. For open addressing, we do need that n is strictly less than m, or in other words, our load factor is strictly less than 1. Okay, so now let's talk about the operations, and we'll assume linear probing when we're discussing these operations. So yeah, assuming linear probing, let's talk about insert first. So or rather, let me map these out. Search and delete. So first, with insert, what do we see? Well, let's say we have some kind of array, or actually let me put an array here for all three. We're going to be talking about the hash table for all three. So, all of these have some slots, and let's say for this first case with the inserting, this slot has been taken, this slot has been taken, this slot has not been taken, and now you're inserting something that that went to index 1, and here you see with linear probing, this slot is taken, so you're going to probe further, and this slot is taken, so you're going to probe the next one, and guess what, this slot has not been taken, so you put your stuff here, and now this slot has been taken, and you're done. You have a successful insertion. Okay, so what about if you wanted to search? So with searching, let's say this spot and this spot have both been taken, and this spot is empty. So let's say or rather not empty, but you know what, actually let's yeah, because there are two cases. There's one where we can talk about something being found, and one case where something's not found. So let's say this, oops, there was something here that was taken, but this spot was empty. First of all, we search something, we search for a key, and it first hashes out to this index. We search here, we don't find it, we probe. We search here, we don't find it, we probe. We reach an empty spot, and we don't even need to go any further, because we know that if it were in the table, then it would have had to have gone in this empty spot, right? It would have had to have done linear probing and gone to this empty spot had it been in the table. But since it's not, it never even existed in the table in the first place. So now we just return. We don't even check here. We don't even check all the way back here. We just return, and it's not found. Now, say we have the case where it is in the table over here. So first, let's say we go here, and it's not found. We go here, it's not found. Then we go here. Well, now we've found it, right? So that's just an example to demonstrate how linear probing can either be used to search where we can short circuit like this, right? We short circuit like this, and it's not found, or we indeed find it. We probe until we actually find it. Okay, so with delete, let's say you have something here, and you want to delete a particular key that's actually located over here. So then what do we do? Well, say something hashed here. Well, the key we wanted to delete is not here, so we look, okay, is the key over here? Well, yes, the key is over here, so we delete it from here. Oops. So we delete it from here, and we write, okay, we've deleted it from here. We don't just empty it out, and we don't just say, okay, it's empty, and that's it. Because if we did that, then imagine if something wanted to probe for some item that was over here, and we wanted to search for this item, and we began searching from here, we went here, and we just short-circuited like we talked about here. In this case where search short circuits, we would have never actually found that when in fact we wanted to. So that's why we have this special delete item, this delete flag that we put into this slot when we're not actually using it. So or rather when we delete something from there and it's free to use by someone else. So insertion can actually find this delete spot and treat it like an empty space, and it'll put something in there. So with insert, it'll find this delete spot and it can insert something there, no problem. But once the empty spot's gone and something's been inserted, there'll always be something in that spot, either an object or a deleted flag, right? Just to make sure that this short circuit case of search works properly. Okay, so that's a lot we've talked about. Now, the question to ask is hash table just the best? Well, once again, we saw that we do get very fast constant time operations compared to the logarithmic time we see with balanced BSTs, and we talked about AVL trees, and those operations were these logarithmic time operations. But once again, we want to emphasize that there are operations that lend themselves towards different data structures, and we use different data structures with different intentions and a different purpose in mind. So if we're never ever going to need to use the predecessor or successor methods, then sure, just for insert, search, and delete, just for these three operations, this data structure, this hash table data structure is probably the optimal data structure to use for implementing the dictionary. But if, say, you do need additional features, then you may either have to augment a hash table or whatever data structure you choose to augment, or you're going to have to find a data structure that meets your needs somehow. So in the simple case we talked about earlier at the beginning of this video with AVL trees, if we do need to use the successor method or rank or select or something, then obviously we would be much better off using just a balanced BST instead of the hash table. So just something to keep in mind while we in our exploration of these different data structures and their applications. So thanks for watching.